In this lecture, we'll do a walkthrough of the LZW algorithm as it will be applied in our coding project. And in particular, we'll start with a much larger alphabet, and we'll look at how to jam codes of odd bit sizes into 32-bit integers, as the project does. Now, our project LZW implementation adds several details to the general LZW algorithm already covered in earlier lectures. First, since we'll be encoding arbitrary data, either text or binary, we'll assume only that our data, our uncompressed data, is some series of bytes, and we'll use as our alphabet all of the 256 possible byte values, plus one more special symbol for end of data, or EOD. This last symbol appears only once, added automatically to the end of our compressed output. We'll talk more about the reason for an EOD symbol later on. Now, the initial dictionary, thus, has 257 codes. That's one code for each symbol in the alphabet, the 256 byte values, and the EOD. Now, this is typical for real-life LZW, but it does invite a confusion. Because of our alphabet choice, the code numbers for the symbols, 0 through 255, are identical to the symbols themselves. Symbol 0, a byte value, has code 0. Symbol 1, a different byte value, has code 1, and so on. EOD has code 256, and that's not really a byte value, so it's a little different. Now, this tends to make students assume that codes are the same as symbols, but this is not so, as is obvious once we start adding codes 257 and higher, which of course will represent symbol sequences. So keep a clean line in your mind between codes and symbols in this project, especially in the initial dictionary. Another practical point introduced in our project, but not in the general LZW algorithm: if you run an LZW compression long enough, the dictionary becomes very large, and you need progressively more bits per code and more space for the dictionary. Also, since LZW in effect samples the uncompressed input for likely sequences of symbols and adds those to the dictionary, if the distribution of sequences changes during the input, say for instance that we shift from one topic and set of vocabulary in some text document to a different one, then the codes that were developed earlier in the compression may not be as useful later on. A common solution to this, and one that we'll use in our project, is to start the dictionary over from scratch after it reaches a certain size, and we'll call this dictionary recycling. And here's a related in-lecture question: what's the relationship between the maximum symbol sequence length for a code and the size of the dictionary? If a dictionary starts with 256 codes, like ours, and then increases to 4,096 codes, let's say, how long can the symbol sequences in it be? Coming back from a pause there. Since it's possible for each sequence to extend the prior one, for instance, if our input is a long repeat of the same symbol, then we might have a symbol sequence of length 2, say, for code 258, and then one of length 3 for code 259, and ultimately as high as length 4096 minus 257 plus 1 to deal with off by one error there. So the maximum symbol sequence could be as long as 3,840 symbols. Now, this will be important in the project since we'll use the code set and memblock types from an earlier lab to hold the LZW dictionary symbol sequences. And we'll want to make memblocks large enough to ensure that any symbol sequence can fit within a single memblock. The output of the compressor and the input to the decompressor will be a series of 32-bit ints. The LZW codes will vary in length per the algorithm, but we'll embed the codes into the ints in the manner already discussed in an earlier lecture on LZW, and which we'll review in the exercise below. This means that the last bits, by the way, of the final int may be unneeded. We'll just set them to 0 if so. So question 2. Say we only need 4 bits of the final int of output to store the last few bits of our final code. We'll set the 28 bits that are left over in that integer to all zeros. Assuming we have no EOD code, what ambiguity would result from doing this? What two or more different ways might we interpret the compressed data in that final int? And coming back from a pause there, we might view those final 28 bits as one or more zero codes, implying that there are extra zero symbols at the end of our data that were not actually in the original uncompressed input. This is an inherent problem in dealing with the final leftover bits, if you insist on having a round number of 32-bit integers as your output. We have to fill those unneeded bits with something, and when we do, there's no way to distinguish between what we meant as a simple dummy filler for unneeded bits and actual codes at the end of the compressed data. The solution is our EOD code, which we add as a final code to the compressed output. The actual input doesn't include any such symbol, and we drop the EOD when decompressing. This unambiguously indicates that any remaining bits after the EOD are to be ignored. So the final output code from our compressor will be the EOD 256 code, and after it, all leftover bits are set to 0 and should be ignored. Now, with all this prologue, let's do a final walkthrough of LZW with the configuration that will apply for our project. The diagram shows the input that we'll compress and the initial dictionary, with the first 256 codes summarized in one line. As you can see, our first output code will be 97, which is the code and ASCII value of the byte containing lowercase a. And we add code 256, representing a B. The next output code is 98 for lowercase b, and we add code 258, representing BA. Here's question 3. How many bits per code are needed at this point? And how soon is that bit per code count going to increase? Coming back from a pause, we have more than 256 codes in the dictionary right off the bat, so we'll be needing 9 bits. And that actually won't increase until we hit code 512, the 513th code, which is well past the range of this example. So everything in the example is going to be 9 bits. Now, we'll worry about embedding these 9-bit codes into 32-bit integers a little later. For now, knowing the codes and that they are 9 bits each suffices. Question 4. Do the next 3 steps of the LZW compress, showing what codes will be output and what will be added to the dictionary. Coming back from a pause here, we're going to add 97 for A and add code 259 for AC, and then we'll output 99 for C and add code 260 representing CA, and then once again a 97 for A and adding code 261 representing AA. So far we've had no luck with multi-symbol codes, but that's about to change. So be sure you understand what we've done so far, and then question 5, obviously, do the next 4 steps. Coming back from a pause there, we can immediately use code 261 to represent AA, and we'll add 262 representing AAA. And then we can immediately use code 262 for our AAA here. Line that up a bit and add 263 for AAAE. And the next one will be code 101 for E alone. We don't have a multi-byte EA code, but we will next time, of course. We're going to add 264 whenever it might be needed, and we'll have an EA code. And then finally, code 261 again shows up for AA here. And we add 265 AAB. Again, a checkpoint here to be sure that we're on the same track. You will want this skill, by the way, because you're going to be debugging your code, and you'll have to kind of piece through the output in the fashion we're doing here. And question 6 then. Do the final 7 output codes, and be sure you see why there are 7 codes needed still. So again, coming back from a possibly lengthy pause here, we're going to output 258 for BA, and we're going to add BAA, and then we're going to output 263 for AAA. I'm sorry, for AAAE, and we'll add 267 AAAEA, and then we have 3 A's here, so we'll output 262 for that, and add 268 4 A's, and then immediately, conveniently, we have 4 A's, so we use our 268 freshly added code, and of course we add 269 immediately for 5 A's, and we use that right away. Now that's 5 codes so far we've done, and I said there were 7. Well, we have a return here, and by the way, apologies if it was not clear, that is a return, single symbol, represented the usual C way. And so the single symbol for that turns out to be ASCII code 10. And so we will output code 10. But then, to be official about it, we could have added a new code, 5 A's and a 10, a return. But actually we're not going to, because we're done with our compression. So if we had more to go, we would add such a code. But we stop at this point, except for one final detail. There is one code we still have to output. If you think about our earlier discussion, that's got to be 256 for end of data. And that will be our final output code. Remember, it's really not part of the input. Okay, that's it for the sample compression, except that we now need to embed these 9-bit codes into 32-bit ints. And we'll do that now. And we'll translate the 32-bit patterns that result into hexadecimal, since the project code will output compressed data in this form, in hex form. And this will enable you to debug project compressed data. That's a major goal of the segment. So the diagram shows how the first 4 codes are compressed here. We have, we have 97, 98, 97, and 99 from our compressed output here, each 9 bits, and collectively they form 36 total bits. Now, to be clear, the bits are grouped by codes, 9 bits each, not ints. To delineate the ints, we've embedded stars at the point between each group of 32 bits. So these 32 bits are our first 32-bit integer output. You need to bridge the spaces between code bit groups to assemble the hex interpretation of those integer bits. Doing that, you can see that, for instance, we have hex 3, 0, 1001 for 9, 1000 for 8, 100 again, 1100 for C, and there's 2 and 6. So our first output int is hex 30988C26. And this is what you'd actually see from your project output. Question 4. Add the next 4 codes to finish the second int and to generate the first 8 bits of the third int. Coming back from a perhaps lengthy pause. This is the diagram you should get as a result. The second int will be 330C160C, and the first 8 bits of the third int here would be hexadecimal 65. And then, of course, question 8, please finish up the task now. And remember to fill in the leftover bits of that final int, and you should find that there are 17 such leftover bits with all zeros. Again, coming back from a pause, the diagram you should get at this point, these final codes and those hex values, and that's finishing the third int right there, and then finishing the fourth int here, and finally the fifth int here with its 17 added 0 bits. See the 256 runs to there, and then these are 17 extra 0 bits at the end. And the hex values, of course, are 6582C080, FO686434, and then 15 and all zeros.